Three-phase half-wave converter. The basic circuit looks like this, whereas this is the three-phase supply and this is the half-wave controller part, and this is our load, which is three-phase star-connected resistive load, where we use T1, T3 and T5 thyristors, and D2, D4 and D6 are diodes. The current flow to the load is controlled by the thyristors, and the firing sequence will be T1, T2, T5, and this is the standard notation for a half-wave controller. Since we are controlling in one direction, this is known as unidirectional controller. This is voltage controller itself. Now the input voltages, that is phase VAN, VBN, VCN, are this. For the current to flow through the power controllers, at least one thyristor must conduct. For a thyristor to conduct, the condition is, first one, that is anode voltage of a thyristor must be greater than the cathode voltage. Second one, it should not be turned on until the current through the thyristor becomes zero. Now we need to find out line to line voltage, that is VAB is given by VA minus VB. So root 2 times of Vs sine omega t minus sine omega t minus 2 pi by 3. And we have a formula, that is sine A minus sine B equals to 2 cos A plus B by 2 multiplied by sine A minus B by 2. So by using this formula, if you simplify this, you are going to get root 6 times Vs of sine omega t plus pi by 6, nothing but VAB, line to line voltage. Similarly, when you find out VBC, it will be root 6 times Vs sine omega t minus pi by 2. Similarly, when you find out VCA, you are going to get root 6 times Vs sine omega t minus 210 degrees, which is nothing but 7 pi by 6. So these are the line to line voltages. Now let us draw phase voltage. This is VAN. VBN, VCN, these are the line voltages of three phase, that is VAN, VBN and VCN. VAB is going to be sine omega t plus pi by 6, which is nothing but minus 30 degrees. So it's going to start here, and the magnitude is, this one is having root 2 times, that one is having root 6 times, which is nothing but 1.732 times more than the maximum value of this. So I'm just considering as that will be more than this. This is VAB. Now VBC is going to start at omega t minus pi by 2, which is nothing but at 90 degrees. Now VCA is going to start at 210 degrees. Operation when VAN is positive, that is 0 to 180 degrees in between, then T1 is triggered and it's going to conduct from 0 to 180 degrees. Then the return path will be shared either D2 or D6 or by both. Similarly, when VBN is positive, that is from 120 degrees to 300 degrees, T2 is turned on and the return path is shared between D4 and D2 or by both. Similarly, when VCN is positive between 240 and 420, T3 is triggered, then the return path will be shared between D4 and D6 or by both. If you observe here, the T1 and the T2 both can come to conduction between 120 degrees and 180 degrees, which is nothing but 60 degrees of difference here. Here also, if you observe, T2 and T3 both can come to conduction in between 240 and 360, here also 60 degrees. If the alpha is less than 60 degrees, from this we can say two thyristors will conduct and the return path will be shared by one diode. When alpha is in between 60 and 120 degrees, one thyristor will conduct and the return path will be shared by two or one diode. If the alpha is more than 120 degrees, then one thyristor will conduct and the return path will be shared by one diode only. If you observe these three conditions, you can observe here the three devices are conducting. Here also there is a possibility of conduction of three devices, that is one thyristor and two diodes. Here two thyristors and one diode. So in this case, the output voltage is going to depend upon input phase voltage. We have another combination, that is one thyristor, one diode, where two devices are going to conduct, in which the output voltage will be half of the line to line voltage between that two devices. For example, if T1 is conducting and D2 is conducting, one is thyristor, other one is diode, then T1 belongs to VAN, D2 belongs to VCN, then line to line voltage between VAN and VCN will be VCA. Then the output voltage will be VCA by 2. When no thyristor conducts, output voltage will be equal to 0. So if three devices operates, output voltage will be equal to the phase voltage. If two devices operates, then half of the line voltage between the two devices. If no thyristor conducts, the output will be 0. From this discussion, we can conclude that the output voltage not only depends on the input phase voltages, but also depends on the line to line voltage of the particular two devices. So the extension angle beta of a thyristor can be increased until this VCA becomes 0 in case of T1 and D2. So T1 is conducting from 0 to 180. Then VCA will become 0 at 210 degrees. So the extension angle we can increase 30 degrees. So the total conduction period of thyristor T1 can be from 0 to 210 degrees. So we need to give a firing signal from 0 to 210 degrees continuous, but in practice we separate this firing signal from 0 to 150 degrees and 150 to 210 degrees. We'll give two pulse signals.